Okay, we've looked at first ionization energy, and you remember what the definition of that was? It was the first ionization energy, let's say for the element X, okay, would be the energy required to remove an electron from a gaseous atom of X to form plus ion. Okay, so that is the first ionization energy. Okay, it's measured in kilojoules per mole. Now, so the second ionization energy would be the energy required to remove an electron from that species, from the single positive ion. So the second one would be X plus goes to X2 plus another electron. That's the second ionization energy. Okay, the third ionization energy would be when you had X2 plus, and you removed an electron from that to form X3 plus, and so on. So you could have, for sodium, it's got 11 electrons, so there are 11 successive ionization energies for when you remove electrons. There are 11 successive ionization energies for sodium. Right, let's have a look at some of those values. So this, I wrote them down earlier. Right, there we go. Okay, now this is for like for sodium. So let's write the electronic structure of sodium, which would be Na. So it's atomic number 11. So it's 1s2, 2s2, 2p6, 3s1. So let's write down the subshell. That's right. So this, which electron is being removed here? It's a 3s electron. Okay, now that's about 496. Now you can see when you go up to the second ionization energy, it's not just a little bit more. You'd expect it to be more because you are now removing an electron from a positively charged ion, whereas the first case you're removing it from something that's neutral. So you would expect it to be more, but it goes up loads. It goes up tenfold. Okay, and we can probably see why. That is because we are removing it from the 2p orbital. Right, now the 3s is going to be somewhere like that. Okay, and 2p is going to be something like that. Okay, so you can see the 2p orbital is a lot closer to the nucleus, and so the attractive force of the nucleus is a lot stronger, and it's harder to remove it. Also, we've got to remember that this 3s electron, this is going to be shielded, won't it? That will be shielded from the pull of the nucleus by all the electrons in the second shell. Okay, so let's have a look at the third ionization energy. Right, and now these are all fairly modest increases. It goes from 4,005 to 6,000. Okay, it doesn't go up loads. 9,000, 13,000, 16,000, 20,000, 25,000, 28,000. But look here, we get a really big jump here as well. So let's explain what's going on there. Well, we can say, let's say, where's the orbital the electron's coming from? This one's coming from 2p. 2p. How many electrons are in 2p? There's 6. So there's 6 there are removed from 2p. All right, and then after that, you're going to start removing it from 2s. And that one's from 2s. Now, why do we get this huge jump here? You can probably see it's because we're removing it from 1s now. Okay, and 1s, I'll draw it in the same diagram there, is much smaller than, much closer to the nucleus than 2s or 2p. And also, it's not shielded by any other electrons, okay, because it's the shell which is closest to the nucleus. So that's why it jumps up massively there. Okay, so you can see when we get these jumps, it's when we're entering a new quantum shell. A new, well, what I mean by that is not a new subshell, but it's not just this subshell that's changing, it's the number in front, the quantum shell. Okay, so there we're going from 3 into the 2s, and here we're going from the 2s into the second quantum shell into the first quantum shell. Sorry about that. New quantum shell here as well. Okay, let's see, can we see anything going on between when here, when there's a jump between 2p and 2s? Can we have a look at that? Well, you can't really, can you? Because, okay, it goes up 4 and a bit. Well, you know, there doesn't seem to be any real jump there at all. So successive ionization energies do provide evidence for successive ionization energies of an element, evidence for principal quantum shells, but they don't give us any evidence for subshells. No evidence for the existence of subshells. Now, if you, sometimes it's easier to see a trend, isn't it, when you plot things on a graph. You can see you couldn't really plot this on a normal graph because, you know, I'd have this value here, 400, yeah, and then like they'd be really small, and then have 159,000. You've got a huge range there. So what people tend to do when you've got a huge range of numbers like that, you might come across it in biology when you're looking at the number of bacteria which are multiplying and they start increasing exponentially. What people tend to do is they use a log scale. So look here, we have got a log of the ionization energy. Now you'll learn about logs later if you haven't learned about them already, but what that means is that number there, this is the ionization energy. That 2.5 means it's 10 to the power of 2.5. That's what, okay, and this one here is 10 to the power of 4 when it's there, and so on. So it has this effect of squashing a very large range of numbers up into a more manageable range, and then we can see a bit of a trend going on in the graph here. So I'll just write down the subshells we're getting these electrons from. So this one is 3s, yeah. These are all the 2p electrons. There's going to be 6 of them. How many have we done there? 5, one more. And then we're going to move into the 2s subshell there. And finally move into 1s, right? And you can see you don't see any discontinuity there here. There's no big jump in the gradient in the graph. You can't really use this as evidence that for subshells, but you can definitely say, you can see whether, you know, there's evidence, this big jump here, the quantum shell, this big shell, a new quantum shell. Okay, let's have a look at some other there's questions that they quite often ask, so I'll just have to get rid of that, make a bit of space. Right, now here's an element, and this is the, I won't tell you what the element is, but I'm going to write down the successive ionization energies of this element. Right, so 1, 2, 3, 4, 5, and 6. I'll go up to. Okay, so we have got 578. These are in kilojoules per mole. 578, 1,817, 2,745, 11,568. 14,041, and finally 18,378. Right, now can you see any big jump? You can see a big jump. There's obviously a big jump here, isn't there, between 3 and 4. So there's a huge jump. The third ionization energy is fairly small, and the fourth is much, much bigger. So what have we done there? We have entered a new quantum shell. So the question is, how many electrons has this element got in its outer shell? Well, it must have 3 electrons, mustn't it? Yeah. Now it's got 3 electrons in the outer shell. It must be in group 3. And I'm copying that out of a data book, and I can tell you that this element is actually aluminium. Aluminium's electronic structure 1s2, 2s2, 2p6, 3s2, 3p1. So let's just write down the orbitals you're getting these electrons from, right? You're getting this one from 3p, this one from 3s, this from 3s, but this big jump here is coming from 2p. You've entered a new quantum shell. It's much closer to the nucleus. There's less shielding because all these ones are shielded by the electrons in the second shell. Well, this electron is in the second shell, so it's not shielded by them. So you can tell which group this element belongs to in the periodic table because you can tell the number of electrons in the outer shell. And this is a fairly common question. They'll give you a load of ionization energies like that, and you have to work out which group is it in. So you look for the jump. Okay, that's it for successive ionization energies then.